So, top of page 2, it says the farmer with 750 feet of fencing wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle. What is the largest possible total area of the 4 pens? This is an example where we can actually solve the problem. So let's review what I call the 4 steps of solving a word problem. Okay. Step number 1, draw a good picture. Step number 2, define your variables. Now you can use any letters of the alphabet, but a lot of times we're using X and Y. Number 3, set up the equation. And number 4, solve the equation. So, for this problem, top of page 2, draw a good picture. So it's a rectangular piece of land. And he wants to divide this rectangular piece of land into 4 pens, right? Parallel to one side. So here's 1 pen. So that makes 1, 2. 1, 2, 3. 1, 2, 3, 4. Okay? So a rectangular piece of land, right, with fencing is going to be divided up into 4 pens. Okay? So let's let X be the width of our rectangular piece of land. And let's let Y be the total length of our rectangular piece of land. Now, so this length, this side, right, of the rectangular piece of land divided into 4 pens, right, is length Y. This side, total length is Y. And then we got 1, 2, 3, 4, 5 sections of fence that are all X feet long, right? So we got 2 sections of fence Y feet long and 5 sections of fence X feet long. And our fencing constraint is we only have 750 feet of fence, right? So we have 5 sections of fence X feet long plus 2 sections of fence Y feet long that have to equal the total amount of fencing we have available, which is 750 feet. So this is our fencing constraint. Okay. That's a linear equation. We can solve for X, right? Or X or Y, right? So Y, so we have 2Y is equal to 750 minus 5X, right? I subtract 5X from both sides. And now when I divide both sides by 2, okay, so I subtract, right? In case you didn't see that, I moved the 5X to the right hand side by subtraction. And now I can divide both sides by 2. And I get Y, the length of the rectangular piece of land. Y is equal to 375 minus 5 halves x. So whatever the width of the rectangle is, rectangular piece of land is, the length has to equal this, right? Whatever the value of x is, this is how we get the length of y. Okay? And meet this fencing constraint of 750 feet. All right. Who wants to know what is the largest possible total area of the 4 pins or the rectangular piece of land? Area is equal to width times length, right? The area of this rectangular piece of land, right, is width, which is x, times length, which is y. And so area is equal to x times y. X is the width, y is the length. And so we can write the area as a function of x when we replace y with what it's constrained to be. It's constrained to equal 375 minus 5 halves x. So we write the area of the rectangular piece of land as a function of the width x by replacing y with what it's constrained to equal. But now if we distribute the x inside the parentheses, we have the area as a function of x is equal to 375x minus 5 halves x squared. And now if I switch these two terms around, I have f of x is equal to minus 5 halves x squared plus 375x. What kind of an equation is this? What kind of a function is this? It's a quadratic function, right? This is like ax squared plus bx plus c, where c is 0. Wait, this is exam 2 material, right? So, what's the graph of a quadratic function? Does this parabola open up or open down? Down, right? So then the graph of this quadratic function is parabola. Does it have a maximum value or minimum value? So we can find the value of x, the width of the rectangle, that optimizes the area. Okay? So there is a value of x that gives us maximum area. Okay? There's a width that gives us maximum area. So this is a quadratic function. And we know how to find the maximum value of it. A is equal to minus 5 halves. B is equal to 375. And C is equal to 0. So, the value of x that maximizes the area, right, is at what is called the vertex, right? Point HK or XY. Okay. So x at the vertex is equal to negative b over 2a. Negative b is minus 375. And 2 times a is 2 times minus 5 halves, which is equal to minus 375 divided by negative 5, right? 2's cancel. Negative over negative is positive, and minus 375 divided by 5 is equal to 75. 75 what? What are the units? Feet. So the optimal width of our rectangle is 75 feet. Do we know what the optimal length of the rectangle is now? We put 375 in for x in our equation for y. So y is equal to 375 minus 5/2 times x. So y is equal to 375 minus 5/2 times 75. And this is one of those cases where writing the answer as a decimal makes more sense because it's a word problem. And so we have y is equal to 187.5 feet. That's the optimal length, okay? What is the largest possible total area of the 4 pins? Well, area, as we already wrote it, it's up over there, is equal to x times y, right? What's x? 75. What's y? 187.5. So the optimal area for a rectangular pen, right, is, so I should write maximum area, right? So the maximum area for a rectangular piece of land is 75 times 187.5, which comes to 14,062.5. What are the units? What? Feet squared, right? So do you write out feet squared, or how do you do it? Put a 2 in a superscript. So you write out feet, FT. You write out FT squared. Is that how you do it? That's the maximum area that you can get from 750 feet of fencing and 4 pins. Every rectangular piece of land contains 4 pins. So when you do the homework, right, you gotta think these things through, right? Draw a good picture. Find what the variables are, set up the equation. Okay? That's what I'm saying. It's only like 5 problems, but you gotta think things through. All right. Any questions on that, ladies and gentlemen? All right. Let's take a look at the next one. It also involves a piece of land. A rectangular plot of land will be fenced into 3 equal portions by dividing fences parallel to 2 sides. The area to be enclosed is 1,000 meters squared. Express the total amount of fence as a function of width x that will be required to build this lot. So there are many rectangles that we can construct that have an area of 1,000, right? But the perimeter, right, is not the same, right? So we got to find the amount of fencing, okay, as a function of the width, right, where the area is fixed. So again, we're going to draw a good picture. And again, right, I let x be the width of the rectangle, right? and y, the total length. But we're going to divide this up, this rectangle, into 3 equal size pins, right? Now, technically speaking, it does not matter how big each pin is. The pins don't have to be of equal size. Okay. So the total length down here of a rectangular piece of land is y, and then we have 4 sections of fencing, each x feet long. Now, the area of a rectangle is width times length. The width is x, the length is y, and the area is fixed at 1,000 meters squared. So this is our area constraint. Length times width, or width times length, is equal to 1,000. And now when you solve for y, you divide both sides by x. You get y is equal to 1,000 divided by x. So whatever the width x is, the total length y has to equal 1,000 divided by x, so that the area is fixed at 1,000 meters squared. Now I should point out over here that the width of each pan is 1/3 times y, because they're of equal width, but that is irrelevant to this problem. Okay. All right. So we have to write the total amount of fence as a function of the width x that would be required to build this slot. So what's the total amount of fence that we need? Well, the total amount of fence that we need is the amount for these 4 sections of fence of x feet long. That's 4x. And then we need fencing for the length, right, for these 2 sections of y feet long. So the total amount of fencing needed is 4x plus 2y. So now if we replace y in our equation with 1,000 over x, we can write the total amount of fencing needed as a function of x. Total amount of fencing as a function of x is equal to 4x plus 2 times 1,000 over x. And that simplifies 4x plus 2,000 over x. So the total amount of fencing needed as a function of x, the width of the rectangular piece of land, is 4x plus 2,000. Now to find the optimal width of our rectangle, okay, we need calculus. So we can't, so this is a problem where we can set up the equation, right, but we can't actually solve it in this class. Okay. All right, any questions on that, ladies and gentlemen? Yes, ma'am.
What's the difference when it says parallel to one side of the rectangle compared to parallel to 2 sides of the rectangle when drawing it?
Say that again.
Like in problem when it says like fencing parallel to one side of the rectangle, and then on the bottom it says parallel to 2 sides. What's the difference?
It's actually, I mean, if it's parallel to this one side, it's parallel
So it's
to both sides. Yeah, it's the same thing. Just expressed differently. All right. So flip over to page 3. Now we're back to working with boxes. A wooden rectangular box with a square base of length x and height h is to have a volume of 32,000 centimeters cubed. Express the amount of wood, S of x, required to make the box as a function of the length of a side of the base x of the box. Okay? So the amount of wood that we need is equal to the surface area, right? The area of the 4 sides of the box plus the area at the bottom of the box. That's the surface area. That tells us how much wood that we need. Okay. So again, let's draw a good picture. We're told that the base or the bottom of the box is square. So the length of the 4 sides of the bottom of the box, right, is x feet. Actually, in the word problem, they call it the length, right? Length x. And h is the height of the box. So this is one side of our open box, right? It's x feet wide, and it's h feet tall, and there's no top. So this is one side of the box. And the volume of our box is fixed at 32,000, right? So how much wood we need in constructing this box depends upon how wide it is, how tall it is. So volume is equal to length times length times height in this case. Okay? Because the base is square. Okay? And so the length, right, x times h is equal to the volume fixed at 32,000. And so we have x squared times h is equal to 32,000. And now we can solve for h, the height, can't we? The height h is equal to 32,000 divided by the area of the bottom of the box, right? The base of the box. The area of the bottom or base of the box is x times x, or x squared. So this is our, right, volume constraint. Now, area of the base or the bottom of the box is x times x, which is x squared, and the area of one side of the box is h times x, and the total area, what we may call the total surface area, is the area of the bottom of the box plus the area of the four sides of the box. On one side is h times x, so the area of four sides is 4 times h times x. But note here in parentheses, there are 4 sides to this box. Okay. So now we can write the total area or the total surface area of the box as a function of x by replacing h with what it's equal to in terms of this. So the total surface area, S of x, is equal to x squared plus 4 times h, which is 32,000 over x squared times x. And now we can simplify a little bit. The total area, which is the total amount of wood that we need, right, is equal to x squared plus, now, this x cancels out one of these x's, and we're left with 32,000 over x. Oops, I forgot something. 4 times 32,000 is 128,000. So we have 128,000 over x. So that is the amount of wood, S of x, required to make the box as a function of the length of the side of the base of the box. And now you need calculus to find the optimal length, right, of the base of the box, okay? That will minimize the amount of wood you need to create a box with a volume of 32,000 cubic centimeters.
So whenever it just says the box or piece, there isn't a limit on it because
Yeah.
Okay.
Yeah, usually if there is a lid on it, it'll say closed box. All right. Any questions on that, ladies and gentlemen? All right, una mas. You'll have everything you need to successfully complete the website homework due tomorrow night. An open box having a square base is to be constructed from 108 square inches of material. So now we have the amount of material. Now we want to see what's the box with the largest volume to make from that. What dimension should be used for the box to obtain a maximum volume? So again, we're going to use the same picture over here. Our base is squared, right? So x is the length of the base, and h is the height to one side. So our good picture is already drawn. Now, the total surface area of our box is equal to the area of the base, which is x times x, or x squared, plus the area of each side of the box. And the area of each side is h times x. And there are 4 sides. So the total area of the 4 sides is 4 times h times x. So this is our material constraint. Actually, I'm getting ahead of myself. The total surface area is the amount of material we have, which is 108 square inches. We have 108 square inches of material, and that is equal to x squared plus 4hx. That's our material constraint. Now, we can solve this equation for h, right? Right, h, the height, is a function of the width, x, right? So we subtract x squared from both sides. We have 108 minus x squared is equal to 4hx. And now we divide both sides by 4x. And we have 108 minus x squared over 4x is equal to h. So when I switch the two sides, I have the height h is equal to 108 minus x squared divided by 4x. So whatever the width, the length, right, of one side of the bottom of the box is, the height is constrained to equal this on the right hand side. Okay. All right. Due to our material constraint, we only have 108 square inches of material. Now we got to maximize the volume, right? Well, volume is equal to length. In this case, we have a square bottom, so it's length times height. We have a square base, so length is x times that, right? Length times length is x times x. And then this is times 108 minus x squared over 4x, right? So now the volume is a function of x. So we can use b of x or f of x, right? Sometimes you use b for volume, but we did in the earlier problem. And so the volume is x squared times 108 minus x squared over 4x. And I can write this as x squared over 1, and when I multiply those two, I have x squared times 108 minus x squared over 4x. So this, I could have left this as x times x and shown that one of the x's cancel out this x. And I'm left with the volume v of x is equal to x times 108 minus x squared over 4. And if you want to, you can write this as 1 1/4 times x times 108 minus x squared. I don't care which way you write it. But that's the volume of the box as a function of the width of the base x. Okay? Oh boy, that dropped the chart. So this actually is a polynomial of degree 3. We haven't studied polynomial functions yet, but you need calculus to find the optimal on x. All right. So you have everything you need to successfully complete the WebAssign homework due tomorrow night. Okay? So I'll see you tomorrow. Have a good day.